Taking a look at that same example, but switching the order of integration, you can really see that there's clearly a better way to do this problem. So let's try and integrate the same solid that we integrated in the last setup, but this time we'll do R first, and then look at the shadow in the z theta plane. So first off, remember that the paraboloid that defines the top is z equals 2 minus r squared. The cone that defines the bottom is z equals r. And that they meet at the shadow that we see down at the bottom, which is a circle. Oops, not a circle like that. We're going to say it's a circle with radius 1 using cylindrical coordinates. Now, to integrate r first, we need to define the bounds for the radius. So we can start at r equals 0 and draw a radius that goes out through our solid. And we can see that on the top half of our solid, the radius is defined by the edge of this paraboloid. So if we solve that paraboloid equation for r, we see that r is equal to the square root of 2 minus z. And we only need the positive square root because we're working above the r theta plane. Sorry, not because we're working above the r theta plane. We're looking at a radius where we define the radius as something 0 and larger. But notice that once we pass this intersection point, the radius is no longer carved out by the edge of that paraboloid, it's carved out by the cone. So we have two separate scenarios. One where r gets to go from 0 to the square root of 2 minus z. That's the top half of our solid. But then the bottom one, r is going to go from 0 to z. And this is what makes integrating with respect to r first in this problem more difficult. Right out of the gate, we're going to have to set up two separate integrals. And remembering that integrating in polar coordinates, the r has an extra factor of r. So we have r dr for that integrand. And then we do our double integral on the shadow. Now the shadow is just allowing us to see which range of z and theta we'll go over. The order of integration that we're told to use says z next, so let's go ahead and take a look at z next. If we're in the top integral, then we are starting at that intersection point and then going above that, all the way up to the top of our paraboloid. And we can see that that will intersect the z-axis at 2. So we do need to figure out the z value of when these two things intersect. There's a few ways we can do it. The easiest way, though, is to see that the cone has to have a radius of 1 to be at that intersection point. So we have to be at z equals 1. Z equals 1 separates the cone and the paraboloid. So when we set up our bounds for the integral for the top half, z will go from 1 all the way up to 2. For the bottom half, however, z is going to start at 0 and go up to 1, that intersection point. And then lastly, we need to think about theta. Theta is allowed to spin all the way around 0 to 2 pi because we're looking at a complete circle. The solid is not being truncated by theta. And then finally, to calculate the actual volume of this solid, not only would we have to calculate these two triple integrals, but we'd have to add them together at the end. So when we are setting up triple integrals, take a look and see if you're setting it up the easiest way. Just like when we first learned about double integrals and type 1, type 2 regions, we said One is sometimes better than the other, depending on the setup. Same thing goes on with triple integrals. Let's take a look at another volume problem with a triple integral. This problem is bounded below by the r theta plane, so the bottom of our solid is the r theta plane, above by the sphere, radius 4, and the sides of our solid are carved out by the cylinder. Now, to be honest with you, I wasn't able to make like a perfect picture of all of these three things merged together, so I did the best I could and I overlaid them. But I want you to think about it. It's not what's between the sphere and the cylinder. Remember that the carved out sides come from the cylinder. So we are going to ignore everything outside of the pink cylinder. We're going to ignore everything below the turquoise plane. And the only part of the sphere that we're going to keep is the little bubble right above our cylinder. So if you can imagine, we've got a cylinder with a flat bottom on the polar plane, but then the top is kind of carved out by the sphere. So it's kind of like a bubble top. It's not flat on top. So we're asked again to set up a triple integral in two different ways. We're going to talk about each of the two ways and then pick the easier one. But if you'd like to see both ways worked out, I believe this problem is in your textbook. So let's think about doing z first. If we set up z first, we could try and define our region by setting bounds on z. We know that z is 0 in the r theta plane, so the smallest value of z would be 0. The top would be when we hit the sphere. So we just need to think about how to explain that z is carved out by the top of the sphere. And we can do that by looking at the equation of our sphere. We have x squared plus y squared plus z squared equals 4. We can solve that for z squared. Remember that we are going to do this in cylindrical, so let's start to convert this over to cylindrical as well. I'll factor out the negative from the x squared y squared so that I can replace that with r squared. And then we know z squared equals 4 minus r squared, so then the top half of our sphere would be the square root of 4 minus r squared. So that would be the top bound for z. That would be if we picked z first. If we picked r first, think about the radius along this cylinder with a little bubble top. The r value is going to be constant for the bottom half while we're in the cylinder, but as soon as we come up to the sphere, we're going to need to define the sphere using a value for r. So we would have to set that up as two separate integrals, and I veto that. I don't want to do two separate integrals. Let's do the easier of the two. We can see that z is consistent throughout the entire solid, so let's go for that. Then we need to do our double integral in the polar plane, so we have r dr d theta. The projection in the polar plane would be like the shadow of where the sphere meets the cylinder and the cylinder meets the plane. It's really just a circle, but that circle is defined by the cylinder x squared plus y squared equals 1. So we have a unit circle essentially. And in that unit circle, we can see our radius goes from 0 to 1. And our theta gets to go all the way around from 0 to 2 pi. And then integrating this is just like integrating that we've done for, 3 semesters now, at least?